this lesson is on set theory and operations. We are going to see how to perform set theoretic operations geometrically. So in this lesson, we are going to see set theory. We are going to see operations using Venn diagrams. We are going to have the sample space and events graphically as a subset of the plane. And in particular, we are going to see what complement is of a set, union, intersection, difference. Also, we are going to work more with events. Last time we saw what an event is. We made clear how to see when we have an experiment, find out what our event is, what our sample space is, because when we start working with probabilities, as we said, the first thing we do, we need to know the sample space and the events. So we are going to see the impossible and certain event, the mutually exclusive events, and finally the collectively exhaustive events. For all these, we are going to work through examples, and so we can see how we can use in practice everything we are going to learn. So, we start with Venn diagrams. These diagrams we are going to use the graphical representation of the sample space and the events are called Venn diagrams. We start by representing our sample space by a rectangle shown in the light blue color. Now, this rectangle is usually used for the sample space, although it's not wrong to use any other, to represent the sample space graphically any other way. Usually, in most books, we are going to see it as a rectangle. The events are represented here with the filled-in orange disk, and assume that this is our event A. Now, the complement of the event A would be the sample space if we take out the event A. How we write this in maths? So, we say that the complement of an event A will be all the elements that belong to the sample space such that they do not belong in A. Note here that we have used this symbol, which this means belong, and this means not belong. Now, we are going to put more events in our sample space and try to do operations with them. So we introduce a new event. We go back to our sample space, our original sample space, event A, and a new event could be event B. Note here that event A and event B could have some common elements. So let's see an example. Assume that S, the sample space, are all numbers between 1 and 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. An event here could be A, the even numbers from the sample space. We have to say here that when we defined an event, we take elements from the sample space. We don't mean taking elements from anything else more generally. So, like in this case, the even numbers we take for the event A are from these 10 numbers. So in this case, event A will be the numbers 2, 4, 6, 8, and 10. The complement of event A will be all elements that belong in S and do not belong in A. So the elements that are left in S and are not in A. In this case are the numbers 1, 3, 5, 7, and 9. Let's go back to our Venn diagrams and see some operations now. First of all, we see the union. We have the union of event A. The first disk is event A, and with the union of event A with event B. The second disk is event B. So the union of these two events is denoted like here and would be the common area of these disks. So we are going to write this mathematically again. In this case, A union B will be the elements X that belong in our sample space, such that the X is in A, or the X in B. We have to say here about the OR. When we say OR, we don't mean exclusively A or B, but not in both. In this case, we mean that it could belong in A and B as well. Let's say again, let's go back to our example and work the union of two events. So we can have another event B, which could be all numbers less than 5. All numbers less than 5. Again, we have to look into our sample space to find the numbers that are less than 5. In this case are the numbers 1, 2, 3, and 4. 5 is not included, as we say less than, and we don't include equal. So A union B will be the elements that belong in A and the elements that belong in B. I am going to write A here again so we can see it. We remember that A are the even numbers, so it's 2, 4, 6, 8, and 10. The union of A and B now will be 1, 2, 3, 4, 6, 8, and 10. We see here that the elements 2 and 4 that belong in both events are also included in the union. Then we are going to see the intersection of two events. We have event A and event B. The intersection of these two events, denoted like here, will be the common area of the two events. So graphically, we have these two disks, and the area that they have in common would be the intersection. Mathematically, we are going to write the intersection as well. So intersection of A and B will be all elements that belong in S, such that they belong in the event A and they belong in the event B as well. In this case, we have and. The elements should be in both events. They should be in event A and event B. Being in one of the two events is not sufficient. So, for our example, I write again event A so we can look at it, where the even numbers, and event B, where the numbers less than 5. So A intersection B will be the common elements of A and B. In this case, are the elements, the numbers 2 and 4. So the intersection will be the set with the numbers 2 and 4. Now we are going to see what the difference is. Again, we have our sample space, events A, and event A and event B. If we have the difference of event A minus event B, we actually mean the part of event A the elements of event A that do not belong in event B. So we actually have the event A, and we have to take out the elements that belong in their intersection. Back to our examples. We have that A minus B will be, in this case, the set A if we take out the elements that belong in A and B. So in this case, we see that B has elements 2 and 4 that are in A as well. We are going to leave out this, and so A minus B will be elements 6, 8, and 10. The event B minus A is different than A minus B. Let's see why. Let's calculate B minus A. The elements of B, 1, 2, 3, 4. We take out 2 and 4 that belong in both, and what we have is a new set with elements 1 and 3. We can see that this is different than this one. It's actually shown graphically as well with our Venn diagrams, as the first difference, the A minus B, is the area here, whereas the B minus A would be the area of B here if we leave out the common part here. Now we are going to see what the impossible and the certain event is. There are two events that they're always in our sample space, and they're very useful when later on we are going to see probabilities. The empty set contains no elements and is called impossible event. Let's see again with our example an empty set, an impossible event. If we define C as the set, the odd numbers, always define events on our sample space. So for this case, will be the numbers 1, 3, 5, 7, and 9. I remind you that A were the even numbers, 2, 4, 6, 8, and 10. So the intersection of A and C, we know that will be the common elements of A and C. We see that there are no common elements, and so this is the empty set. It's the impossible event, as we say. It is impossible, of course, to have an even number and an odd number at the same time. The certain event. If we have, let's go back to see first what the certain event is. S is the sample space. It contains all elements and will be called the certain event, the event that will happen certainly. So For our example, A union C will be all odd and all even numbers. So it will actually be numbers 1 up to 10. It will be S. We know that if we put together the odd and the even numbers, of course, one of these is going, if we pick one number of these, one, of course, is going to be from here. It's going to be from our sample space. It's the certain event. Now we are going to see a bit more with operations using Venn diagrams and see how we can practically use them when we have examples. Mutually exclusive or disjoint are called two events that do not have common elements. We see that they do not have any area in common. So we have event A, event B, they are called disjoint. If we have more events that they do not have any common elements with any other events, they would be called mutually exclusive. Using mathematics, this can be written as A intersection B, we see, is the empty set. A intersection C, again, no common elements. A intersection D, no common elements. B intersection C, no common elements again. And C with D is the empty set. So these events are called mutually exclusive. In our example, we have seen that A intersection C is the empty set, so they do not have any common elements, and they are called mutually exclusive or disjoint. If I go back, remind you B, which was numbers less than 5, I write here B is the elements 1, 2, 3, and 4. We see that A intersection B will be the common elements 2 and 4. This, of course, is not the empty set, and so A and B, in this case, are not mutually exclusive. They are not disjoint. Another property we are going to see in the events is when they are collectively exhaustive. We have our sample space S, and we have the event A is part of our sample space. Also, another event B here, and another event C here. All these events, we can see that if we take their union, if we put them all together, their area will make all sample space. These are the events that are called collectively exhaustive. So In the example we have seen, collectively exhaustive events would be A, B, and C. Write down again A, I write down B, and C. And so we see that A union B union C is our sample space. And these are called collectively exhaustive events. We note here that even A union C would make our sample space, and so A and C are collectively exhaustive, but that's no problem. This as well makes S, so these are collectively exhaustive as well. Also, another property is when we have both collectively exhaustive and mutually exclusive events. In this case, we see that our events A, B, and C, if we put them together, their union, give us S. But in addition, they do not have any common elements. They are mutually exclusive. In this case, we have again, as we said, that the union makes S, but also the intersection would give empty set between A and B, between A and C, and between B and C. In our previous example, A and C are collectively exhaustive and mutually exclusive, as their union makes S, and their intersection is the empty set. There are no common elements between A and C. In this case, though, we see that A and B, the intersection is not the empty set. So they don't have both the properties A, B, and C. Now, we see here that A, B, and C, their union is the sample space. And finally, we are going to see the example of rolling a die. We said that we are going to have the sample space, which is numbers, elements 1, 2, 3, 4, 5, and 6. And we assume that, we say that event A would be elements 4 and 6. Also, we write event B as the elements 1, 3, and event C elements 5 and 1. Another element is 2 in our sample space. It doesn't have to belong in an event. We are not interested about it, so we do not put it in an event. And now we are going to do some operations with this. We see that the intersection of A and B and the intersection of A and C is the empty set. There are no common elements between AB and AC. We better write this down so we can see this clearly. So when we roll a die, our sample space, as we said, is consisting of elements 1, 2, 3, 4, 5, and 6. We have event A, which consists of elements 4 and 6. Event B consists of elements 1 and 3. And event C of elements 1 and 5. The intersection of A and B is the empty set. There are no common elements. The intersection of A and C is again the empty set. No common elements. The intersection of A and of B and C would be element 1. This is not the empty set. So these are mutually exclusive events, disjoint events. These are also mutually exclusive events, disjoint events, but these are not. They have an element in common. The union. The union of A and B will be, if we put all elements together, the set that contains 1, 3, 4, and 6. The union of B and C will be the elements 1, 3, and 5. Consist from elements 1, 3, and 5. It doesn't matter that 1 belongs in B and C as well. We said that when we have the union, we have all elements that belong in B, all elements that belong in C, and also the common elements as well. Let's see the complement of one of these events. Let's take event A. The complement of A, we said, would be the set that contains all elements that belong in sample space S and do not belong in the event A. We have to look at our sample space. We need to know exactly what our sample space is. And if we leave out the elements of A, the complement of A will be the set that has the remaining elements. 1, 2, 3, and 5. Now, events A, B, and C are not collectively exhaustive? They are not, because if we write their union, we see that we have element 1, element 3, 4, 5, and 6. Looking back at our sample space, we see that we are missing element 2. And so A, B, C are not collectively exhaustive. We are going to see graphically again all this. We said that the intersection here of A and B, A and C, is the empty set. C and B have one element in common, and it is obvious that the three sets, the three events, are not collectively exhaustive. They do not cover all sample space S. One element is left out. It should be included so that we have all sample space S. So, today we have seen how to work with sets, how to do operations with sets, and we have seen all this graphically using Venn diagrams. We saw operations using Venn diagrams graphically. What is the impossible and the certain event? What are mutually exclusive events? And finally, collectively exhaustive events. The two last properties are very important properties, as we are going to use them a lot when we do calculations with probabilities. For more information about this lesson, you can visit the web page of UNINETTUNO MED-NetU project.